So now that we've completed a look at molar mass, let's take a quick look at molar volume. And this is actually where it all goes back to that sexy beast of a man, Avogadro. So if you remember from our notes on molar mass, remember that Avogadro, when he was learning about, what a mole was, he was actually playing with gases. And he found that no matter what gas you could have nitrogen gas, you could have hydrogen gas, you could have a mixture of gases. If you have a gas, and no matter what gas you have, and you hold it at the same temperature and pressure, that gas will actually have the same number of molecules as any other gas at that temperature and pressure. This is what he actually said in written form, is all gases at any specific temperature and pressure will contain the same number of molecules. So if you always have, say, 1 atmosphere of pressure and the temperature is 10 degrees Celsius, no matter what gas you have, you hold it to that pressure and that temperature, that gas is going to take up the same number of molecules. We can take this a step further with a condition known as standard temperature and pressure. When we deal with gases in chemistry, we'd like to hold our gases to a standard temperature and pressure. And this standard temperature and pressure we call STP. STP is the temperature of 0 degrees Celsius and a pressure of exactly 1 atmosphere. So what it would feel like to stand outside on a regular day. And what's cool about standard temperature and pressure is we found that because you have the same number of molecules of a gas, it's going to take up the same volume. So at STP, 1 mole of any gas takes up exactly 22.4 liters of space. So if you have a gas at standard temperature and pressure, no matter how much you have, 1 mole of that gas is going to take up 22.4 liters. And this lets us solve problems. So here are our 2 practice problems with molar volume, and they're pretty straightforward. So the first one says, what volume of space would 5 moles of hydrogen gas? Remember, hydrogen gas is a diatomic gas, so it's actually H2. What volume would that take up at STP? So we know that we have 5.00 moles of hydrogen. This is just like before. And we also know that at STP, this is key, 1 mole of any gas, we're trying to get rid of moles here so it goes on the bottom, takes up 22.4 liters. So it's simply 5 times 22.4, which after I put it into my calculator equals 112 liters. So I know that if I have 5 moles of hydrogen gas and I hold it at STP, it's going to take up 112 liters. And of course, we're going to double check for sig fig. There's 3 here. This is a conversion factor, so it's infinite, and we're also going to have 3 sig fig there. In the second problem, we're going to go the other direction. We have helium gas at STP, and it fills a balloon. The balloon comes to a volume of 10 liters. Therefore, how many moles of helium are in the balloon? So this time we go the other way. We have 10, the decimal's important there, 10 liters of helium. And we know that for every, get rid of liters, put moles in, for every 1 mole at STP, let me erase that real quick, we have 22.4 liters. So it's just 10 divided by 22.4. Put it into our calculator, and we get this long number that's 0.4464, and it goes on and on. Check sig fig. This decimal is important, meaning there's 2 sig fig. Conversions are infinite. So we're going to round this to 2 sig fig, and we're going to get 0.45 moles of helium gas. And that's all there is to it. So finally, we have this problem that combines both mass and volume. We have iodine gas at STP, and it fills a container with a volume of 73.80 liters. So we're going to start with the 73.80 liters that we have. And since we know we're at, I'm going to put liters there, and it's I2. Since I know we're at STP, I know that if I have 22.4 liters of a gas, I have 1 mole. And this is going to give me 73.80 divided by 22.4. And it's going to give me 3.2946, and on and on and on. But this is actually not mass of iodine. This is grams of iodine, or moles of iodine. So we're going to have to convert it to grams. And the way we do that is we multiply it by the molar mass. So I know if I have 1 mole of iodine, getting rid of moles, I have, and I've got to look it up in the periodic table. So the mass is 126.905 times 2, because there's 2 iodines, so it's 253.81 grams. And when I multiply that out times 3.2946, I get 836.2 grams of iodine in this container. I can then go back and take this number for moles right here and solve the second problem, knowing that I have 3.2946 moles of iodine. And I know that getting rid of moles, if I have 1 mole of anything, I have 6.022 times 10 to the 23 molecules of that thing. It's molecules all scribbled out. So if I go to 3.2946 times 6.022, I get 19.84 times 10 to the 23. That's improper notation, so I'm going to make it 1.984 times 10 to the 24 molecules of iodine. Finally, the last one is how many iodine atoms, and I know that if I have 1.984 times 10 to the 24 molecules, and I know that in every molecule, so 1 molecule of I2, I have 2 atoms of iodine. That's going to give me 3.968 times 10 to the 24 atoms of iodine. And that's it.